All right, chapter 5 is serial communication. So before this, right, we communicate. We use the microcontroller to communicate with other device. But that device is simple devices, right? Simple device. For example, the switch for the input, the push button for the input, the LED for the output, the LCD for the output. All right. So there is a way to communicate between the microcontroller and that device. All right. So the easiest way is to just connect the wire, right? Like this. Okay, let's go back to this. Okay, so if we have the microcontroller, okay, and we want to communicate with other devices, for example, another microcontroller, right? Microcontroller to microcontroller. And our data is 8-bit, 8-bit data. The easiest way is we have our data in the register R0, for example, and the data is 8-bit, A0. So the easiest way is to use to connect the wire through the output pin to the IO pin. All right. So we have 8 wires. 3, 4, 5, 6, 7, and 8. Right. So this is pin number 0, 1, 2, 3, 4, 5, 6, 7. Okay. And just send the data to the pin. So A0, so can be something like this. A is 1 0 1 0 0 0 0 0. So the logic at this line is 1. The voltage level is 1. The voltage level for this line is 0 1 0 0 0 0 0. And here, of course, the second microcontroller will get or will receive this data at the input pin here, right? Input pin here. So we can read directly, okay, in R0 also. Straight away we can get A0 inside the second microcontroller. All right. So the sending data from one microcontroller to another microcontroller or other devices is actually very easy. Connect straight away. And this is called parallel data communication because we send data parallelly, all right, in parallel. All right, if our data is 8-bit, so we send 8-bit at a time, right? When a new data coming, A1, for example, the line will be A1, and the second microcontroller will receive A1. Okay, but the problem with this parallel communication is that, what is the problem? Anyone? it is costly, right? Because you need 8 wires for 8-bit data, and you need to use 8 I/O pin. All right. So your microcontroller, the embed, for example, you have how many I/O? The embed, you have 40 pin, but for the I/O pin you have only 30, right? Now you use already 8. All right, use 8 already for just to send the data. So it is waste of resources. Yeah. So the parallel communication is very costly. Okay, so there is another way to send the data to other devices, which is serial data communication. We send serially, yeah, where we use only one line, right? So if we have, this is microcontroller, this is microcontroller. So we use minimum one line only, all right, to send the data from this microcontroller, from the first microcontroller to the second microcontroller. All right, serial communication. So this one, we can reduce the cost significantly, and only we use one pin, right? But the problem is, now what is the problem with serial communication or drawback? Anyone? Right, so this is parallel communication and this is serial. So what is the drawback of the serial data communication? Of course, first thing that we can notice is that it's slower, right? Because this one time you can get 8-bit already. Okay, this one, once you put your data on the bus here, on the line here, immediately this microcontroller, the second microcontroller, will get the data. But for serial, you need to send bit by bit. All right. So if your data is 8-bit, it means that this is 8 times slower. Another issue that we need to deal with is that how do we know? How do we know? Or how the second microcontroller recognize the data or interpret the data? All right. For parallel communication, the data is easily interpreted. All right, because this is 1, because this line is 1, this is 0 because this one line is 0. But if for serial communication, your data is sent like this, again we use the same number, 0 A0, right? So A0 in binary is 1010 0000. Okay, so in the line, the voltage level in the line, if you probe using the oscilloscope, what you will see is something like this: 1 0 1 0 0 0 0 0. All right, so far so good. But the problem is, how do the second microcontroller know that this is only one bit? not 1 1. All right, because it can be 1 1, right? 1 1 or 1 1 1. And how the microcontroller know that this here, how many 0? 5 0. All right. How the second microcontroller know that here is 5 bit or 5 0? Because you see here only 1 0, right? All are 0. How the microcontroller know that this is actually you have 5 0 here? That is the issue with serial communication. But the advantage is, of course, the cost. And people are looking for lowering cost. Low cost is good. So you need to know we have two communication method. One is parallel communication. The second one is serial communication. What is the problem with parallel communication? The cost. All right. Parallel communication is easy. All right, easy to implement, but the main problem is the cost. All right. So we have another kind of communication method, which is the serial. Okay, but the serial, the main problem is how the two microcontroller or two parties or two devices understand each other. All right. When one microcontroller send the data to the second one, how the second one understand the data, all right, determine read the data. Okay, so that is the issue. Okay, so to solve this problem, there are two kind of serial communication. All right, the first one we call asynchronous serial communication, and the second one is synchronous serial communication. Okay, so this will solve that issue. All right, the data interpretation issue, synchronous and asynchronous serial communication. So we will look at synchronous serial communication first, the synchronous. So how we describe the data in synchronous serial communication? We use what we call, the name is synchronous, means that we use clock, all right, to synchronize the data. Okay, so for example, we still have A0, 1 0 1 0 0 0 0 0. So you will have 1 0 1 and 0 0 0 0. Okay, so what you need to have is, this is data, and you need to have clock. All right, okay, something like this. So let's say we read the data every positive clock edge. So here, 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 and here. All right, so here means that 1, here 0, here 1, here 0 0, and then you have 0 0 0. All right, so you use clock to synchronize your data. Okay, so what you do is, this is your reference. You use clock as your reference. Okay, this positive edge, we read the data. So 1, another positive edge, we read the data. 0, another positive edge, we read the data. 1, The next positive edge, we read the data 0, 0, 0, 0, 0. All right. So if we send this clock and this data to the second microcontroller, and in the second microcontroller, we agree or we program that to read the data this way or synchronize with this clock. So the second microcontroller, we know exactly the data is actually a 0, 1, 0, 1, 0, 0, 0, 0, 0. So that is to solve the problem, how to recognize the data. All right, get the idea? So this we call synchronous serial communication. Means that when you want to send the data serially to the second microcontroller, what you need to do is you need to have at least one data line and one clock line. Okay, so you have two, but this is better as compared to parallel communication. You need to have 8. All right. Okay, good. So now that is the idea. Okay, so for the further reading, you can read from the notes. Yeah. Okay, so this is the same principle. Yeah, we synchronize the data, the serial data with the clock line. Yeah. So for example, this is bit 0. So meaning that the data is 1 here, is 0, 0, 1, and so on. All right. So that solves the problem. Okay. Now let's go further. Let's see the how we implement this in microcontroller or in electronic devices. All right. So how the serial communication work? All right. So actually the data, okay, if you want to, for example, if you have two devices like this, and one we set as master like this, and the second one we set as slave. But we want to send the data, the master want to send the data to the slave or node 2, all right, and want to receive, So we have two lines, all right, two lines. One is for sending, okay, SDO. SDO is serial data out, serial data out. So serial data out here to the serial data in the second microcontroller or slave, all right. And this one is serial data out for the slave, and this is serial data in for the master. All right. So you need to have separate line. All right. So this is, if you learn communication, right? Data communication. This is called simplex communication, right? Data is one direction. Okay. And this is line for clock, right? So in this case, you need 3 wires or 3 lines, right? So how the data is transferred? Okay, for example, this is data coming, serial data in. We read the data from the slave. Okay, so you need to have a register, and of course, your microcontroller has a register inside, right? So, and of course, we have many register in the microcontroller. So, and how the data is entering the shift register, the register we call shift register, because the process is something like this. Let's go back to this so that you can see how the things work. Yeah, so you have the register, and let's draw our register here. So the register is just like R1, R0 in chapter 3. Okay, so you have a register. And this is 8-bit register, for example. Okay, and the data is again A0. So A0, the data is 10100000. So how your microcontroller receive the data? So it receives the data like this. So one will go first. All right. So you have one in the LSB. Okay, and then you shift. All right. The next clock cycle, you shift again. So you have 1 0. The next clock cycle, you shift again. You have 1 0 1 until you have all 1 0 1 0 0 0 0 0 0. Okay, that is how this thing works. Shift register. All right. So that's why you learn shift register in digital design. Yeah. So this is where the shift register used to receive or to send data serially. One of the use of shift register. Yeah. So you shift the data from the right to left. Yeah. And when you want to send the data, you shift it out, shift data out. Yeah. So from the MSB, you shift to the serial data out. And here is the receive for the slave. All right. So that is how the system work. How the system work. All right. Any question? Okay. So if no question, so we proceed to the next. All right. So let's look at the example of serial communication, synchronous serial communication. So we have two type of synchronous serial communication. The most popular one, the first one is the SPI, or serial peripheral interface. The first one, and the second one is the let's go to the second one. This one, the I2C, or integrated circuit. All right. So these two are the synchronous serial communication. So let's go one by one. All right. Go to the SPI first. So in the SPI, we connect our microcontroller with other devices like this. So in this case, we have 4 slaves. All right. This slave can be another microcontroller or other electronic devices. For example, sensors, LCD, and other electronic devices. So how do we connect all this? So we have this SDO, serial data out, serial data in, exactly like this. And we have clock. So we have 3 liners, just like this, right? 3 lines. Okay. So you can see that all the slaves share the same bus, right? Share the same bus. Means that if you send the data, all of the slaves will receive the same data, right? But we don't want that. So how to make sure that, for example, we want to send the data from microcontroller to slave number 2. How to make sure that only slave number 2 receive the data, but not slave number 1, number 3, and number 4. Okay, so we have another line, another wire here to activate which one we want to activate. All right, for example, if we want to activate this, and here we have SS. SS is slave select, and you have bar here means that it's active low. So when you send 0 and others are 1, means that only this one is activated. So this one is the one that we want to communicate or want to send the data to or want to read the data in, right? We use this as line, or sometimes we use CS, CS or chip select, all right? So depend on the chips that you use when you open datasheet. Sometimes they call SS or sometimes they call CS, chip select. All right. So how the things work? Let's how to use this in embed. So the working principle is actually the same with what I have explained just now. SPI actually the data inside the line, the transmission line is exactly like this for the SPI communication. So let's see how we use the embed microcontroller to implement the SPI serial communication. So this is the function, all right, SPI format frequency write, and see what to do. Okay, so in embed we can have up to 4 modes, 4 operating modes to send the data. All right. So this is SS. When it's low, right, means that we activate the slave. And for mode 0, if we select mode 0, which is default mode for the embed microcontroller. So this is the clock. SCK is the clock. The clock. So the clock in here, when the system is idle, means that there is no data to be sent. The clock is low, all right, logic low. And when we want to send the data, the clock is activated here, all right, for mode 0. And this is the data. For mode 0, we will read the data at the positive edge of the clock, all right. So this is mode 0. Idle, mode 0, idle, the clock is 0. And when we send the data, the clock will be activated and we read the data at every positive edge of the clock, all right, or rising edge of the clock. So that is mode 0. What is the difference between mode 0 and mode 1? So mode 1, this is the clock, but mode 1, when we use mode 1, we will read the data every falling edge or negative edge of the clock, all right. That is the difference between mode 0 and mode 1. For mode 2, when idle, the clock is high. The difference between mode 2, 3 and 0, 1 is that when idle, mode 2 and 3, when idle, the clock is high. Mode 0 and mode 1, the clock is low. All right. That is the difference between these two and these two. For mode 2, when idle, the clock is high and we read the data. Data stroke means that we read the data at the negative clock edge. All right, negative clock edge. Negative we read, negative we read. What about mode 3? Mode 3, when idle, logic high for the clock, and we read the data at the positive edge of the clock. All right. So that is working principle or how the data is read in SPI interface. We have 4 modes. To declare the object name, and we need to use the SPI function. SPI, this is object name. So object name can be any name of your choice. All right. And the pin. Okay. So before that, let's look at our embed microcontroller. embed LPC 1768. This is the embed. All right. So let's see here. So this is our embed microcontroller. This is SPI. So we have how many SPI for this one? We have two SPI interface. Yeah. So this is serial in, this is serial out, this is output, this is input, and this is clock. All right, so we have two. So in this case we use this port, P11, P12, and P13. All right, in this example. So you can always use this one also. Okay, so let's go back. So here we use P11 as MOSI. MOSI is master out, slave in, master out, slave in. MISO P12 is MISO, so this is MISO P12. P1 is MOSI, master out, slave in. This is master in, slave out. P12 and P13 is for your clock. All right, and you need to define your SS or chip select. In this case, I use CSS, chip select. So chip select is set at P14. All right. So in your microcontroller, so here you use for MOSI, P12 you use for MISO, P13 SCK clock, P12 we use for digital IO, digital out, which will connect to the disk. All right. So in this example, we will have only one slave, one slave. Okay. Now we want to set the format of our SPI data transfer. So to use the format, to set the format means that the mode, the mode. All right, the mode and the size of the data, and by default is actually mode 0 and 8-bit. So this is how the we set the format. So support is actually this one, our name. So if you name it other name, so you need to use that name. So dot format. All right, 8 means that your data is 8-bit, and 0 here is mode 0. If you want to use mode 1, so this one must change to 1. And the frequency of your clock is 1 megahertz here. All right, so this is the frequency. And CS equal to 0 means that you select the slave, select the slave. And how to send the data? Very easy. Your object name support here, dot write means that you want to write or want to send the data. And if you want to send character A, for example, this is ASCII character A, and ASCII character A, when you open the ASCII table, it is actually 41 hexadecimal. So this is how you send 41 or A to the serial communication line. All right, and wait for the other side to receive. Okay, this is for slave. So if you want to send a data from microcontroller to microcontroller, so one must be a master and another one must be a slave. All right, so in the slave part, when you want to receive the data, this is how. Okay, so again, this should have space, to change in your notes. So this is how you write the code to receive the data from another microcontroller. So slave, if you want to use the same pin, right? For example, you want to use this one also. Okay, so P11, P12 for master out, serial in, slave in, P12, P13 for clock, and now your SS or CS is included in this bracket, P14 for receive. If you look at for at the sending part, the microcontroller for the send part, your slave select is different. You need to declare different using digital out. All right. So SPI is only this, only 4. Why you need to why you need to have this? Why you cannot include here? Because you may have many slave. All right. So if you have many slave, you may have CS1, CS2. So you need to have many digital out declaration. But for this one, slave, it is only one slave. All right, in slave part. So it is included in this declaration. Yeah, that is the difference. And of course, you need to have the same format. Means that your both microcontroller must speak the same language. All right. So if you set the first microcontroller to use 8-bit data and mode 0, so the second one must use the same format. If not, the second microcontroller will not understand what the first microcontroller sent to it. All right. So make sure that you use the same format. And in this case we use 8 data bit, and the size of the data is 8, and the mode is 0, and of course the frequency also very important. The frequency must be the same, which is in this case is 1 meg. All right. And at the receiving part, you need to wait for the data to come, right? Wait for the data to come. So how to wait? So you need to use if. All right. So if support dot receive equal to 1, all right. So this means equal to 1. If equal to 1 means that the data is coming. All right. So this is how you read. When the data is coming, you read. So how you read? You need to declare variable, whether you want to declare as char or float, depend on you. All right. So this is the variable. So you read the data to the variable at the receiving part. So how to read? Very easy. Your variable equal to support dot read. Read. Then you read the data to the variable. All right. So that is how to use SPI in your embed microcontroller. Okay. So this is the sending. When you want to send, you need to write the code like this. When you want to receive, you need to write the code like this. Right. Now let's look at the example. Any question so far before we go to the example? Okay. All right. Or maybe you can ask later, or you can just refer back to the video. I will upload the video on YouTube. Okay. If no question, so let's go to the next example where we write the program for the setting like this. So I draw the setting for you first so that you can get the idea. So let's run. Okay. So let's go back to this. Okay, so let's, for example, we want to have something like this. We have two microcontroller. First one, the second one. All right. We want to send the data using SPI. Okay. So we'll have this is for serial data out, this is serial data in, or master out, this is master out serial in, this is master in serial out, and another one is for the clock, right? So this will be master out serial slave in, so the same, yeah. This is master in slave out. So this is SCL. So this is the master. This is the slave. Right, we want to do this. Okay. And try to send the data from the master to the slave. Okay. And we will use the oscilloscope to see how the data inside looks like. Yeah, inside the line looks like. And also the line, the clock line. Okay. So let's go back to the code. So this is the code. All right. Of course, you need to have your include embed.h. Yeah. Use the embed compiler. So SPI. So this is our function. We want to use SPI function. So underscore port. So our name SPI object name. And we use P11 for master out serial in, P12 for MISO, and P13 for clock. Yeah. And switch word, we have declare one variable named switch word as char. All right. Data type char. And this is our main loop for our main program. So this is the setting. Yeah, the format is 8-bit and mode 0, and the frequency of our communication is 101 megahertz. Okay, and now let's see, we set the switch word equal to 41, or in this case is character A. Yeah, character A, and we send. So how to send? Based on what we have learned just now, support.write. So we send this thing, and this is 41. So we send A, and we wait 5 microseconds, and we change the value in switch word to 45. 45 is actually not B. 45 is E. Yeah, E. To change this in your notes, this is not B. This is E. Okay. So we send E. All right, this is send and wait, and because this is inside the while one loop, so means that it is loop endlessly until you switch off. Okay, until you switch off. Okay, so what you do is actually you send 41, you send 45, go back 41, 45, 41, 45. All right. So when you run this program, yeah, when you run this program, so and when you tap the data out line, you can see this, and when you tap the clock line, you will see this. All right. So let's look at this. So this is a clock. Yeah. So here you see when there is no data, the clock is not activated. All right, means that idle. And we use mode 0, right? Mode 0. So when idle, the clock will be 0 or logic low. And when we want to start here, okay, so the clock is activated and we read the data, we will read the data at the positive edge, right, of the clock. So what is the positive edge? In this case, positive edge is, right, so here, right, so positive edge. So the first is 0, is it? First is 0, all right? And the second one, the second clock, this is the second clock. And when you look at the second clock, this is 1. This is 0, and this is 1. So 0, 1. And the next one is 0, 0, 0, which is 4. Right? Remember, we send 4, 1. Yeah? We send 4, 1. So 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0 is 4. And look at this. 0, 0, 0, 0, 1 at the end. So this is A actually. Right? So this is A. Right? Based on this. So if we have clock, you see, yeah, when we have clock, we can easily interpret the data. We know exactly this is A based on what? Based on the clock. All right. But if we don't have this, we don't know what is this data, whether this is 0, 0, 1, 1, 1, 1, or whatever, can be anything, right? But if we synchronize with the clock, we know exactly. Okay. So look at the second one. The second one, the first positive edge is 0. The second positive edge is 1. All right. We have the first one is 0. And the second one is 1. All right. Next one is 0, 0, 0, which is this is which is 4, right? And the next one is, again, this is 0, 1, 0, 1. What is that? So this is 4, this is 5, right? 0, 1, 0, 0 is 4, 0, 1, 0, 1 is 5, which is E, the one that we send exactly. Okay, the data that we send exactly 41, 45. This is 4, 1, this is 4, 5. All right. So that is how the SPI work. Okay, any question so far? And this is what if we look at the logic analyzer, yeah. So this one is on the oscilloscope, so you can use logic analyzer as well in the lab to see the data. So exactly we can have A and E and A and E, right, for this program. Okay, so that will be the first example. All right, we will go to the next if you don't have any question to ask. Let's look at the second example where we have something like this. So let's go back to here. All right. So we have something like this. Let's see, we have, okay, use the same example here, only that we have the switch connect to this, the master. Okay, we have the switch. We have to switch, and this connect to the supply. All right, so we have to switch. Okay, and we have, this is too big. Let's redraw a little bit. Okay. Okay, so we have these three lines, of course, and the sleeve we connect to the LED. We have LED. We have two LED. Okay. The first one is red LED. So I have red LED. The second one is green LED. Okay, so we have setting just like this. Now what we want to do is when we press this button, all right, we will read, the master will read that this switch is pressed, and we send the data to the slave, and the slave will turn on the red LED. When this switch, the first one, let's name it SW1, this one is SW2. When we press SW2, the green LED will turn on. All right, means that we need to send the data that we read from the switch through this communication line to the slave, and the slave receive the data from this and send the output to the LED according to what it received from the master. All right. Okay, so let's go back to this. Okay, so what we do is we declare our program like this. So again, we use SPI support, the name. So this one can be any name, in bracket P11, P12, P13, just like before this. So for this one, and we have this one is for just ignore this first, because this one is designed for receive as well. So this is connected to the LED also, but for this example, let's remove this so that you're not confused with what I have done here. All right, I think should be better here. So, and the chip select SS is connected to P14, just the same with the previous one, and the switch. All right, the switch name is switch IP1 or SW1. We name it in our drawing. So connect to P5, P5, and this is digital in, and the second switch is connected to P6, and we have this one. Just remove this first. Okay, on this, and this is the main loop. All right, this is the main loop. So we have switch word here declared as char data type. So you have A0, all right, A0 here. You assign to this switch word, and you test the switch here. When switch 1 or IP1 equal to 1 means that it's pressed. So what you do this. You switch word, you take switch word, and you OR with, this is OR, yeah? OR with 0, 1. So what you have here, because your switch word you have A0, and you OR with 1. What you have here will be what you have here will be something like this, because your switch word initially has A0, right? So A0 is 10100000 in binary, and you OR with when switch 1 is pressed, so you need to OR with 00000001, right? So you OR this, you will have 10100001. Okay, so when switch 1 is pressed, you will have switch word equal to this. All right, and when switch 2 is pressed, here, when switch 2 is pressed, so what you do is switch word, which is A0, you need to OR with 02. All right, this is the case for SW1. This is for case SW2. So you will have 10100010 in your switch word. All right. So next, what we do is okay. Right. What we do is we select CS equal to 0, means that we select the slave. We send 0 to the slave, means that the slave that connected to our microcontroller will be activated, and we send the data. So this is how to send the data. All right. Support equal to dot right switch word. This is to send the data. All right. Okay. So this is for just ignore this part. Yeah, this part is for receiving part for the master, but we don't want to implement that for this example. So just skip this. All right. So that is for the master. Now look at the slave part. All right. So this is the slave part. So the slave. So we will have SPI slave like this. Slave support here. We use the same port. P11, 12, 13, 14 is for the chip select. And this is the output. So we use the digital out. Connected to P25, connected to P26. All right. This one is just ignore again, because this one is also used to send the data, but in this case we don't want to do that. All right. This one you just remove for now. We don't want to use also. So let's have this only. So to receive, this is how we receive. We check whether the receive is equal to 1 or not. So to check is easy. If support.receive equal to 1, so we receive, we read. So we read to this value. So this is how we receive. We check whether the data is received or not. So if received, what we do is, yeah, we off the LED and here, all right, we and the value that we receive, the value that we receive with 3, all right, with 3 here, and we on the LED according to what we have received. So let, for example, yeah, let's for example we press switch SW1. So what we will have is something like this. When, for example, SW1, we press SW1, okay, so we will send this to the master out serial in. We will send this value, meaning that we will send this. One zero one zero 0001 to the master out serial in line. All right, and of course with the clock. Okay, and the second microcontroller or the slave will receive this value, and this value is here. All right, is here. Okay, and we end with 0 3. All right, so when switch 1 is pressed, so we will receive 1 0 0, sorry, 1 0 0 0 0 1, and we end with 3. Okay, we end with 3 0 0 1 1. So we will have 1 and 0. We have 0 0 0 0 0 0 0 1 here, right? So this is what we get. When we press SW2, what happened? When we press SW2, we will send oh, I haven't showed this, right? Sorry for that. Again, I repeat, yeah. When we press SW1, what we do is we end what we receive at the slave. So we receive this at the slave and we end with 3. So we will get 1. When we press SW1, what if we press SW2? When we press SW2, we will send 10100010 to MOSI, and we will receive in the slave at the slave is this value. And what we do? We end with 3. So again, what we receive is 10100010. We end with 3 0011. So we will have 00000010. When we press SW2, we have 10. When we press SW1, we have 1. All right. So that is the case. So let's go back to the program. So you see here, if if the value here that we n already here equal to 1, we turn on the red LED. The red LED equal to 1. If the value is equal to 2, which means that the SW2 is pressed, right? Equal to 2. This case. This case. All right. When equal to 2, this case. So we turn on the green LED. But if both are pressed, means that 1, 1. So both LED are on. 1, 1. All right. Okay. That is how the program works. Again, I repeat. So what we want to do is this. We have two microcontroller connected like this. This one is made as master, and the second one is the slave, and we connect using SPI. The first one, the master, is connected to the switch SW1 and SW2, and the slave is connected to the LED red and LED green. And when we press SW1, we send this value to the slave, and we filter this value out such that we have only this by using n. We end with 3, so that we can on these two LED according to this. So when we have received this, means that the green LED will turn on, right? Because this one, when we end with 3, we will have 0, 0, 0, 0, 0, 0, 0, 1, 0. So the green LED will turn on. When we send, when we press switch 1, so we will send this value, and when we end with 3, so we will have 0, 0, 0, 0, 0, 0, 0, 1. So this LED will turn on. So why we do this? We need to OR, we need to AND. So this is for demonstration that if I send only one value, for example here, when we look at the on the oscilloscope, we cannot see the pattern. Yeah. All right. So to see the pattern, so make the data more complicated so that we can see the pattern. All right. So that is why we OR to have this value on the line so that we can see the value. All right. And to control the LED, so we remove the unwanted value and just remain the value that we want to use and on the LED. Okay. So that is how the things work. So I will show you the hardware setup. Yeah. Of course, you cannot use this because you don't have the hardware, and also in the embed simulator you cannot use it because embed simulator you cannot use two microcontroller like this. Yeah. But this is for your understanding. So I show the hardware. So where is the setup? So this is the setup. Okay. So the connection is this. You have two microcontroller. Hope you can see this. Yeah. Two microcontroller, and this is the line. Yeah, the link between the we use jumper wire here. Link to the second microcontroller. All right. So this is a SPI P11, 12, 13, and 14. Connect to the same P11, 12, 13, and 14 for the slave. So this is slave, this is master actually. And I also connect this this board, actually the oscilloscope, electronic oscilloscope that you can connect to your computer using USB, and you can see the on the screen the signal. All right. So I tap the value of the data and also the clock to see on the oscilloscope. So you can go back to that. All right. And also I connect to the, this is a switch where you can actually simulate on your computer. I will show you later. And this is the LED where you can simulate also the on your computer using the software that included with this oscilloscope. All right. So the the setting is something like this, and we will see on the monitor screen. Yeah, I have with me now, so I will show you the. This is the signal on the oscilloscope. All right, so I will show you in real time by having this. Right, do the connection. So this is the oscilloscope. Is it connected? All right. So I try to connect to the. Okay. Now I have two microcontroller with me, and this is the signal on the oscilloscope screen, real time. All right. So let's pause. So this I have the static I/O here. So this is the switch where you can set using this one. You can set whether you want to set this as a switch, and this is connected to bit 30 on the board. So if you look at the board here, this is connected to this 30 and 29 here. All right, for the switch 30, and the LED is connected to 0 and 1. So if you look at this, so should be these two. All right, 0 and 1. So when SW1 is press, this means press. 0 is not press, 1 is mean press. So I press, so the LED is on here. So you see it blink because we have wait function 0.01 second. So it's quite blink because of that delay. All right. When I press the second button, so you have this on. All right. When you not press, you don't have. When you press both, I have both on. All right. So let's see what happened on the oscilloscope when you not press anything. All right, the scope. So it will be the previous value that you have. So let's press one button, the first switch, this switch. So we expect that we will send 10100001, is it? All right, because the switch 1 SW1 is pressed. So okay, so let's see. So we have the clock here, which is 10100001 exactly. So this is when we press switch 1. All right. When we press switch number 2, okay. So what we have here is 10100010. Means that we send this value to the second microcontroller, to the safe. All right, when we press switch 2. All right. So that is how this program, this example work. Yeah. So if you can access to the lab, so you can see this actually on the oscilloscope, which is quite interesting, quite fun. So when you do the project later for final year project, so you can actually debug or see what is inside your line, your wire. When you face a problem, right? So you can see actually whether the data is sent or not, right? And the data is correct or not, right? By using the oscilloscope. Okay, so that is for the SPI. All right, for this program. Okay. Any question for SPI? So we are done with SPI actually. All right, good. If no question, we proceed to the next I2C, and I think that's for today.